So question number 5 says, according to Newton's third law, when two objects interact, they exert forces on each other. Which of the following statements is not a correct description of these forces? Okay, so for Newton's third law, the key points are the forces must be of the same type, they must be in opposite direction, they must act on different bodies, and they must be acting at the same time, and they must be equal in magnitude. Now we can see here that the forces, they act same time, okay, same direction. That's not true. They have to act in opposite directions. Okay, different bodies, yep, same magnitude, yeah. So it's going to be B. Okay, so that's the answer to this. Let's move on. Question number 16, we're talking about a space probe that's sent to Mars. So as the probe approached the surface of Mars with a vertical velocity component of 460 meters per second, a parachute was opened to reduce the speed of the probe. Once the vertical velocity of the probe had reduced to 75 meters per second, the parachute was removed and the thrusters were switched on. Due to an error, the thrusters were switched off too soon, leaving the probe to free fall to the surface of Mars. So this is when we have the parachute. This is when we have the thrusters and they're on. And this is when we are in free fall. Okay, so these are the three situations. So part A says to us, the parachute was used over a decrease in height of 9.7 kilometers. And they want us to show that the average vertical deceleration of the probe due to the parachute was about 11 meters per second square. The reason it's saying average is because when the parachute is there, the acceleration won't be constant. It would be changing. So we need to find an average of it basically. Okay, so we're going to use SUVAT for this question. So SUVAT. So I'm going to take the direction down as positive and up as negative to make things easier because everything is moving down. So displacement is going to be 9.7 times 10 to the raised power of 3. Our initial velocity was 460 meters per second. Our final velocity is going to be 75. Acceleration is what we got to find out. Now for this, the equation that we can use is v squared is equals to u squared plus 2as. So v squared minus u squared over 2s is equals to 8. So after you plug in the values, you're going to get the answer as minus 10.6 meter per second square. I'm going to put that minus in bracket. That's going to be approximately 11 meter per second square. Part II of the question, it says the parachute was at an angle to the vertical as shown. The total resistive force acting on the parachute and the probe was at an average angle of 6 degrees to the vertical. Calculate the magnitude of the average total resistive force. Again, it says average because the resistive force will change over time, and when we consider the entire situation, we can take an average for calculation purposes. And then it says, you may neglect the mass of the parachute. They've given us the mass of the probe and the gravitational field strength on Mars. So for this, you're going to make components. Actually, before we make components, I have one more thing. Let's talk about that. Now, the parachute and the probe both are moving downwards with a velocity v. Even though they're moving downwards with a velocity v, the acceleration is actually upwards. I'm going to say that up is negative and down is positive. That's going to be my sign convention. So my acceleration by this sign convention becomes minus and my velocity becomes plus. Hope that's clear. We're going to come back to that. So I'm going to make components of my force. So it's going to be like this. So we're going to have F for the average total resistive force, cos 6, and this is going to be F sine 6. This is similar to what you do in projectile motion when you make two components of the velocity. Now I'm going to be looking at the vertical side of things because that's where I have more values at. So we have one more force in the vertical direction, that's going to be the weight. Now that we have done all of that, now we can use Newton's second law to make an equation. We're going to get mg minus f cos 6 is equals to ma. I'm going to make f the subject, so we're going to end up with, so I've moved this term to the other side and this term to this side and made f the subject, so we're going to get an expression like this. I'm going to factor out the m, so we're going to get g minus a over cos 6. Now I'm going to plug in the values. This is going to be 3.8 positive. This is going to be the average deceleration vertically that we calculated. And this is going to be minus because it's acting up. So minus 10.6 and then the mass they've given to us. So I'm going to plug in the values. So we're going to get a value of 8,687.6 newtons. To 2SF, that's going to be 8,700 newtons. Now we're going to be looking at the final part of this question, which says the probe was in free fall from a height of 3.7 kilometers, reaching the surface of Mars with a velocity of 150 meters per second. Explain whether the term free fall is correct in this context. Your answer should include a calculation, and they've given us the gravitational field strength on Mars. So free fall means that the force of gravity is the only force acting on the object. Now here the probe, when it's in free fall, it's going to experience resistive forces. And because of that, it's not going to be in free fall. But we can't simply write that, we have to also support it with a calculation. So I've written down the first 2 points that I said. An object in free fall has only the force of gravity acting on it. The probe will have resistive forces acting on it as well. Now the next thing we're going to do is we're going to show this using calculation that the probe is not in free fall. So we're going to get the acceleration first due to gravity on Mars as 3.8 meter per second square. Now we're going to find the acceleration of the probe in the actual situation and see if it matches up with this value. So we're going to use SUAT again. Alright. Same thing again, I'm going to take down as positive and up as negative because everything is acting down. So we're going to have 3.7 times 10 to the raised power of 3. And then we're going to go back and see the diagram here. So this is when the thrusters are switched off, so 68. And then the object falls supposedly in free fall and reaches 150. So this is going to be initial, this is going to be final. So let me just write that down. So initial is going to be 68, final is going to be 150, acceleration is going to be question mark. So we're going to write our equation. That's going to be v squared is equals to u squared plus 2as. V squared minus u squared over 2s is equals to a. So let's plug in the values and get the answer. So we're going to get the value of acceleration as 2.42 meter per second square. So we can clearly see that 3.8 meter per second square is greater than 2.42 meter per second square. So the object, or not the object, the probe is not in free fall. Okay, 2 reasons. One is that there are going to be resistive forces, and second, to support this statement, we have also seen that the acceleration also doesn't match with the acceleration due to gravity on Mars. Okay, so that's going to be the answer to this question. Now I'm going to show you the MS and E